Merci Philippe Aubert pour la présentation et l'introduction. Ça a beaucoup de signification pour moi que tu aies fait ça aujourd'hui. Donc, bonjour à tous. J'ai appris que Paul McCartney est en ville ce soir et demain. Donc, c'est une grosse compétition pour moi. Alors, merci du fond du cœur d'être là ce soir. Okay, so I'll switch to English. My presentation is going to be on sound field control, engineering applications. Maybe I need to say upfront that what I am going to present tonight is not my work. It's primarily the work of the many students who worked with me on this topic, including Philippe Aubert. And this is going to be the outline of the presentation. I will try to explain what is sound field control, what it is used for, and I will present some of the main approaches to do sound field control: inverse methods, wave field synthesis, higher order ambisonics. I need to say here that as a scientist, as an engineer, I'm going to use some mathematics in there, very minimal mathematics, I hope. So I hope you enjoy mathematics. If you don't worry, just ignore the equations, and I'll try to make my explanations as clear as possible. And the main part of the presentation is going to be about applications, and this is going to be engineering applications. And the main applications I'm going to cover are for, let's say, natural sound field reproduction, aircraft cabin sound reproduction, workplace sound fields, and I'll explain why we did that. The next applications will be about metrology, the process of measuring things in acoustics or in vibroacoustics. And I'll try to show you that sound field control can be very useful to do some very nice measurements in acoustics. And the last application will be about oralization of models, which is the process of making models audible. Okay, so a little history to start with. On the left here, you have the title page of a report that was made for VRQ, which was Valorisation Recherche Québec. This is a project that took place in 2004, so not long after CIRMMT was created. And the project was about, you see the title, it was about transmitting and reproducing using immersive systems, both video and audio content. And the project involved Vislav, Dan Levitin, Ichiro, Jeremy Cooperstock was involved, and myself was involved. And on the right part here, you have a wave field synthesis system that was borrowed from Fraunhofer in Germany. It was installed in Vislav's lab here at McGill. And this was the beginning of Philippe Aubert's thesis in 2005. So it was also for me the beginning of the journey. And when I was first exposed to these systems, I told myself there have to be fantastic things in engineering to do with these systems. And the journey began at that time. And I need to say that probably none of what I am going to present would have existed without CIRMMT. CIRMMT made it possible. So what is sound field control? Sound field control is the process of reproducing using a loudspeaker array. I'm going to limit myself to loudspeaker presentation in this presentation. So it involves reproducing using loudspeaker arrays over an area as large as possible, a sound field that can be either a natural sound field, which has been captured using microphone arrays, or a spherical microphone, for example, or it can be a virtual sound field, which is made of monophonic sources, which are assembled and distributed virtually in space. And this process involves usually an encoding step, transformations, and a decoding step. What is it good for? Sound field control? Well, probably you know about that. It's used in immersive audio, virtual reality, augmented reality, spatial sound, artificial reverberation. It's also used more and more for some multi-zone audio applications in vehicle cabins, in automotive. Multi-zone audio in automotive is about to come. It's also used in public spaces, in museums, and so on. Active noise control, active noise cancellation can be considered one form of sound field control where you cancel one sound field with another artificial sound field. And oralization also. Oralization, which is, again, the process of listening to models, to objects which do not physically exist, which exist in the computer. Oralization is a form of sound field control. So when dealing with sound field control, it is important to distinguish between spatial sound perception and spatial sound reproduction. So a few techniques like stereo, surround 5.1, 7.1, and so on, all these techniques work to mimic spatial hearing, our spatial hearing system and its limitations. For example, by creating phantom images. In contrast, spatial sound reproduction works to recreate the physical stimulus, the sound field, the sound pressure distribution in space. So it's a fundamental difference between the two approaches. And again, in order to implement spatial sound reproduction, there are a few methods. These are the three that we have used and studied in Sherbrooke. So I'm going to briefly cover the fundamentals of these methods. Inverse methods, wave field synthesis, and higher order ambisonics. Here comes the maths, a little maths. So this is a brief summary of inverse methods. So the problem here, assume you have a target sound environment which has been captured using an array of microphones. The inverse method will try to build this big filter here, H, which is going to be used to drive reproduction loudspeakers in such a way that these reproduction loudspeakers, which are set up in a possibly totally different environment than the natural sound field, will create the same, or as much as possible, the same microphone signals on the same microphone array as the one that has been used to capture the natural sound field. So this is the problem. And here I have introduced an important quantity here, which is the G, which is the transfer functions between each of these reproduction loudspeakers to each of these microphones, propagation paths. Okay? So in essence, this inverse problem is a minimization problem because what you want to achieve, given the target sound environment, you want to derive the source inputs such that the target sound field is as much as possible identical to the reproduced sound field. So the subtraction of the two sound fields is as small as possible. This is a minimization problem. And in engineering and in science, we love minimization problems because we have tools to solve them. So these are the solutions. There is a solution. I'm not going to spend a lot of time describing the equation, but what is interesting to see is that this solution involves inverting a system, inverting this matrix of propagation paths between all of these loudspeakers and all of these microphones in the listening space. Okay? You will want to invert this matrix. You will want to compensate for this propagation. And in acoustics, as soon as you invert something, things go wrong. Things go wrong. It doesn't work. Why? Because you will drive some of these loudspeakers like crazy. You will saturate them probably. And because the result will be probably very sensitive to measurement noise. You will amplify measurement noise. So this simple solution does not work in practice, and what you have to do is regularize the solution. And again, I'm not going to spend details to explain details about that, but you will pay a price by which you will lose some accuracy of the solution by regularizing the solution. But it's absolutely necessary. So to summarize, inverse methods. The pros, this work for any propagation operator. In other words, the listening space can be anything because you will want to compensate for the acoustics of your listening space. It's not necessarily free field. There are many tools available to regularize the system or to minimize, to solve for the minimization problem. The cons, results can be very sensitive to how you regularize. And in practice, this requires a large system identification. This big matrix of transfer functions from all loudspeakers to all microphones is a very big task to identify. Wave field synthesis, this is the second approach. It's a much more physical approach of doing things. The inverse is a brute signal processing approach. Inverse wave field synthesis is much more physically based. It's based on fundamental principles of acoustics, and mainly the Huygens principle. So Huygens principle, what is it? Huygens principle, probably you should know about that. Suppose you have a source here, a loudspeaker that creates spherical waves. The Huygens principle states that you can reconstruct the next wavefront by ignoring the primary source. You forget about the primary source, and you assume that the previous wavefront behaves as a distribution of secondary sources. Okay? So all these sources on the previous wavefront behave as secondary sources to construct the next wavefront. And this can be applied in a straightforward manner to sound field reproduction. Again, if you want to reproduce the sound field from this primary source, you can use a line or a surface of loudspeakers, and each one of these loudspeakers will create a velocity, an acoustic velocity, which is the acoustic velocity created at this point by the primary source. That's what Huygens says. I'll skip the equations here. All what this slide says is that, as usual, things are not that easy. So say you have a primary source that you want to reproduce, or any combination of sources on the left part of this plane, okay? And you want to reproduce the sound field created by any source on the left part, and you want to reproduce it on the right part of this plane. Then in theory, you will need a full wall of loudspeakers on this plane to do that. But in theory, if you have a full wall of loudspeakers, you can recreate the sound field of any source on the left part. The reproduction will work at any point on the right part of this plane. A full wall of loudspeakers is not very practical. So in practice, most wave field synthesis systems work with line arrays of loudspeakers. And the price you pay by using a line of loudspeakers instead of a full surface area is that the reproduction will work only in the horizontal plane, and even not everywhere in this horizontal plane. This is taken from Philippe Aubert's thesis. Actually, these are examples of wave field synthesis results. This is for a point source, which would be located around here, just below the x-axis. This is the real part, the imaginary part, and this is what wave field synthesis would reproduce using a line array of reproduction sources on this red segment. Okay, and you see that you correctly reconstruct the wavefront from the point source virtually. And this also worked with so-called focused sources, that is, sources between the loudspeaker array and the listener. So this is an example for point source at this location. The reproduction system will work by creating converging wavefronts to this point, and then from there, the wavefronts will diverge from this virtual source position. And any listener sitting in this area will have the impression that the sound comes from this position in space. So wave field synthesis, in summary, it can create a large valid reproduction area, large sweet spot. There are commercial systems available. Cons, 1D arrays provide only an approximate solution in the horizontal plane. 2D arrays are expensive. And all this theory works theoretically in free field. That is, wave field synthesis reproduction will include artifacts that are created by the acoustics of your listening space. Reverberation of your listening space will create artifacts, which are not usually dramatic in terms of spatial impression, but they're there. And this actually shows the adaptive wave field synthesis system that was developed by Philippe Aubert during his thesis. So this specific system compensates for the reverberation of the listening space. Okay, moving to higher order ambisonics and some more mathematics, and that will be the final equations I'm going to use here. I hope you know this equation. This is the wave equation. That's the most important equation in acoustics. Turns out that when you try to solve the wave equation in spherical coordinates, you get this awful expression, this awful equation. So here, just to make it clear, R is radius, theta is azimuth, and delta is elevation. And K is frequency. Okay, so what this equation says that the solution of the wave equation in spherical coordinates is a summation of these spherical harmonic functions, which depend on azimuth and elevation. weighted by these blue coefficients, which are called ambisonic coefficients. And it turns out these spherical harmonic functions have a strong physical meaning. And I have plotted the first few of these spherical harmonic functions. This is a monopole. These are dipoles along the three coordinate axes. The next ones are quadrupoles and so on. So this expression provides a multiple expansion of the sound field at a given position in space. So in essence, what this equation says is that if you know these coefficients are the signatures of the sound field at a given position in space. If you know these coefficients, you can use this equation to predict the sound field around the position where these coefficients are known. And one of the problems is that this sum is infinite, and in practice it never can go to infinity, which raises problems. And the problem is that this what this slide says is the previous equation will work in a fairly small region of space, okay, which is this region here. And it turns out that as the frequency increases, this sweet spot becomes smaller and smaller. Okay, so this is one of the main limitations of HOA. And in order to estimate or measure these blue coefficients, these ambisonic coefficients that I showed previously, you are going to use a spherical microphone. So this is the simplest form, the sound field, which is based on 4 capsules on a tetrahedron. It can measure the ambisonic coefficients up to order 1. And you can use more sophisticated microphone arrays like this rigid sphere, which has 50 microphones, can measure ambisonic coefficients up to order 5. And you're probably familiar with other systems, Zilia, Eigenmics, or other commercial systems to record ambisonic coefficients. And this is the last step of HOA, which is decoding. Decoding is what you need to do in order to drive the loudspeakers of your reproduction system in order to reproduce the ambisonic coefficients that you have measured on a natural sound field in another environment and that you want to reproduce using your loudspeaker system. This is the 50 loudspeaker system that was built by Pierre Lecomte during his thesis, 50 loudspeakers, 2 meters in radius approximately. And so the decoding step essentially involves this matrix operation. If you know the ambisonic coefficients, you can derive the source inputs that will create the same ambisonic coefficients at the center of the sphere using this operation, which involves a reoccurring matrix, which you need to invert. Again, no surprise, you have to invert something. And this is usually, again, where things go wrong, and you need in practice to regularize, equalize, and so on. So, summary for HOA. The channel count in HOA system is usually not as large as in wave-field synthesis. I have not talked about that, but you can apply spatial transformations of the encoded sound field, like rotations, or impose artificial directivity. The cons, the sweet spot is usually limited by your ambisonic order, and it's physically smaller as frequency increases. It requires regularization and equalization at encoding and decoding steps. And again, the source inputs are theoretically valid in free field. So like wave field synthesis, HOA presentation will include artifacts that are related, that are due to the acoustics of your listening environments. Okay? I don't know how I am with respect to time, but I'm shifting now to applications. And this is the first applications I'm going to talk about. This is for aircraft cabin sound reproduction. So why do we want to do that? The project was done, actually, Catherine was involved in the project. Philippe Aubert, there's a lot of Philippe Aubert in this presentation. Philippe Aubert was involved, he was the champion behind this project. The project was done with Bombardier, with CAE here. And Bombardier, for example, when they want to document the acoustic comfort of an aircraft cabin, and this applies mostly to jet aircraft, not passenger aircraft. So it's very specific market, business aircraft, because in jet aircraft, people want a lot of comfort, including acoustic comfort. So Bombardier, when they want to document the acoustic comfort of their aircraft cabins, they use numbers, they use curves, they use sound pressure levels, and so on. But for a customer, that doesn't tell anything. So nothing, and this is true actually for many, many applications in engineering. Nothing replaces the experience of actually listening to the real thing. So that was the idea behind this project. Plus, Bombardier had mock-ups of their aircraft cabins. So these are full-scale mock-ups that they bring to shows and events and exhibitions, which are exact reproduction of the interior of the aircraft that they show to potential customers. And so they wanted to add the acoustic dimension in these mock-ups. So it started by something which turned out to be quite complicated, was to measure, to capture the sound field inside an actual aircraft, CRJ 1000, Bombardier, in flight. And this was done using, it's quite small here, it was done using a rectangular microphone array, 80 microphone array. We used, Julien, I think, was involved in these measurements. We also used a binaural head and an eigen mic here also. So I have, I will try to make you listen to So this is a signal taken from one of the mics of the array, and this was during taxi, so not in flight, and the pilot played with the throttle. And what we hear here is mostly the engine sound. So in flight, what you are going to hear inside an aircraft cabin, most of you, I'm sure, have made this experience, you will hear essentially the aerodynamic noise, which is due to the airflow, turbulent airflow around the fuselage. This turbulent airflow drives the fuselage structure in vibration. This vibration radiates sound inside the cabin. This is actually the main source of noise inside the cabin. It's low frequency, below 1 kilohertz, mostly. You will hear the engines, mostly tonal noise. You will hear the climate system, ventilation system inside the aircraft. You will hear some auxiliary systems, pumps, and so on. Yeah. So And this is the mock-up that was installed at Sherbrooke. It's a two-seat rows mock-up. It's absolutely identical to the actual aircraft. This is a CRJ 900 mock-up installed in our lab. We installed the same microphone array at the same position inside the mock-up. And the objective was to recreate as much as possible the same microphone signals at all of these microphone positions in the mock-up. And to do that, we used a number of actuators which are shown in this picture. These are not loudspeakers, actually. These are small shakers that were mounted on the trim panels of the mock-up, which are the same trim panels of the actual aircraft. In other words, we used the trim panels as the loudspeakers. 36 of them, plus a subwoofer, plus 4 bass shakers on the floor to drive to include some vibration content also, not just purely acoustic content. And this is what we obtained. This is an example of frequency spectrum. The green is the target, or this is the in-flight measurement, and the black is the reproduced spectrum. So we did quite well in terms of the frequency. And this is an example. This is what we actually achieved spatially in the mock-up. So these two are the target. So the small dots here are the microphones of the arrays, and this is the sound field at a specific frequency, 424 Hertz, and this is what we reproduced in the mock-up. So the reproduction was quite accurate, both in terms of the frequency content and in terms of the spatial distribution inside the mock-up. We also did some listening tests. I will skip this because for benefit of the time. And this is the next application I wanted to talk about. So we did essentially the same for workplace sound fields, this kind of environments. I'll make you hear an example of this. This one. And I'll play this one. Which is this one here. So what you hear is a reverse alarm on this truck. This is a special type of reverse alarm. We heard the reverse alarm also in this capture, which was a tonal, beep, beep, beep. This one is broadband. And the reason we captured and studied these two specific environments is because these reverse alarms are a real source of concern for people like IRSST, the Health and Safety Institute, which is very close to here, because workers on the field in environments like this sometimes cannot hear these alarm sounds or cannot locate correctly the alarm sounds. And there are accidents each year, and workers getting killed each year. So the idea was to capture these environments using this circular microphone array and reproducing them in a laboratory environment and demonstrate that it's possible to recreate these complex environments in a lab setting. Why? Because doing some listening tests and subjective tests on these with these reverse alarms, it would be much easier in a lab environment than in an environment like this or like this, obviously. We did this with the wavefield synthesis system that is in Sherbrooke, using the same circular microphone array. And this is an example of result. So this is an example of a frequency spectrum. Again, the green one is the target, so this is natural recording, and the black is the reproduction. So in terms of frequency, this is the overall sound pressure level for all the microphones of the array. So we had some problems with some microphones in the field, and you can imagine that these environments are very tough, very harsh. So it's no surprise some of the microphones did break up. And this one is a little bit difficult to understand, so I'll try to make it clear. Philippe Aubert called them bimograms. So this shows time here. These are dynamic environments, varying as a function of time. And this is azimuth. So this is the direction of the incoming sound as post-processed from the microphone array. And this is the target, this is the natural sound field, and it is the reproduced sound field. And I want you to concentrate really only on this line here. And this is the alarm sound. This is the broadband alarm. Psht, 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 psht. And you see that it's moving in space, it's moving in azimuth because the truck moved during that recording. And it's correctly reproduced in the lab. So the reproduction was able to recreate this impression of the sound from the alarm coming from the correct direction in space. So this was one of the main results of this project. Next application is for metrology. So these multi-loudspeaker systems are actually very nice tools for doing measurements in acoustics, and I'll try to explain why. And the first measurement we'll explain is transmission loss measurement. So transmission loss is a measurement that provides the insulation performance of a given wall or glazing or aircraft structure. So transmission loss is by how many dBs the sound is going to be decreased when crossing a panel, a structure. It turns out that these transmission loss measurements are usually done in coupled rooms. So this is a coupled room facility. This is the one at Sherbrooke. Reverberant room on one side, you make noise, you make a lot of noise, you create a diffuse field, and you place your structure in this wall, and you measure the sound transmitted on the other side using an intensity probe. So this requires a coupled room. This is very costly and complicated infrastructure. Turns out that we are also interested sometimes by measuring the transmission loss of panels not under diffuse acoustic field conditions, but under turbulent boundary layer excitation. I mentioned the the example of the aircraft. It's a good example where the aircraft structure, the fuselage structure, is excited, is set in vibration by a turbulent flow. There are pressure fluctuations in this turbulent boundary layer outside. These turbulent pressures will drive the fuselage in vibration, and this will radiate sound on the other side. So in order to measure this in a lab, you need an anechoic wind tunnel. You create a grazing flow over a panel, and you will measure what is transmitted on the other side. Very complicated infrastructure. So the idea here was to do that using an array of loudspeakers placed close to, parallel to the structure you want to test. Okay? And these loudspeakers are driven in such a way that you recreate the statistics of a diffuse acoustic field or the statistics of a turbulent boundary layer on the panel, on the surface of the panel that you want to test. And the beauty of this application is that you don't need a full array of loudspeakers. You just need one loudspeaker. Because if you measure transfer functions between this one loudspeaker and many vibration points on your structure, and if you move your speaker then to the next position and repeat this measurement of transfer functions, all the reconstruction and all the synthesis of your diffuse acoustic field or turbulent boundary layer or anything will be done at the post-processing stage inside your computer. So you don't need to do it physically. You just need one loudspeaker. This is the virtual source antenna concept. So we did that. We did that for diffuse acoustic field excitation. So we compared the classical method using the coupled room, reverberant room, anechoic room, and we repeated this with the virtual source array, source antenna. So we just had one monopole that moved in front of the panel, and the panel vibration was scanned using a scanning laser Doppler vibrometer, and this vibration measurement, we use it to reconstruct the sound field on the other side. And this is an example of result. This is the TL, the transmission loss in dB as a function of frequency. So it's not very clear, but the gray is the coupled room measurements of the TL, the transmission loss, and the blue is the synthetic diffuse acoustic field obtained with the scanning monopole. This is for 35 source positions, so we move this loudspeaker to 35 positions, and we repeated, well, not me, the student, PhD student, repeated that for 345 source positions. And you see that as you increase the number of source positions, the result will coincide with the coupled room measurements, the one you would get under true diffuse acoustic field. So works. And these sound field control techniques can work also for other measurements in acoustics, such as sound absorption coefficient measurements. So in acoustics, you know it, you often use sound absorbing materials, fibrous materials, foams, and so on. These materials are, the absorption properties of these materials is quantified by an absorption coefficient, which is the ratio of the absorbed energy to the incident energy. And this measurement, according to the standards, should be done, well, at least one of the standards should be done under diffuse acoustic field conditions. So you put a fairly large amount of material inside the reverberant room, and you measure the reverberation time of this room without the material first and with the material, and the difference between the two reverberation reverberation times will give you access to the sound absorption coefficient. There are major issues with this standard. One of the problem is that you will measure sound absorption coefficient that can be well above 1, which does not make sense. Sound absorption coefficient should be between 0 and 1. And it varies a lot from one reverberant chamber to the other. So again, we used very similar type of sound field control, sound field reproduction techniques using, again, the virtual source concept with just one monopole facing a small amount of material. And in this case, we used you can see it here, we used a microphone pair just above the material surface. And what this microphone pair does is it's going to separate the incident and the reflected wave and give you access to the sound absorption coefficient. So by moving just the one loudspeaker at many positions and letting the computer do the sound reproduction work, you will be able to synthesize the sound absorption coefficient of any material under synthetic diffuse acoustic field. And this is an example of a result we got. This is the reverberant chamber measurement. So the absorption coefficient goes well above 1. This is what we obtained. The triangles is what we obtained with the synthetic diffuse acoustic field. And the ground truth here was taken to be a simulation, actually. Simulation, numerical simulation for some materials are very accurate. And this is what the simulation gave. So quite close to what we actually measured using the virtual source antenna method. Okay, it turns out you can do also that for plane wave excitation. Okay, not only diffuse acoustic fields are interesting, also plane wave. You can easily recreate an perpendicular plane wave above material. You can do it in an impedance tube, so it's very easy. But it's very complicated to fabricate an oblique plane wave. And we did that actually using a full array of loudspeakers on a material. So these many loudspeakers were used to create a plane wave at any incidence angle above the material surface. And it turns out we obtained sound absorption coefficients that again were in very, very good agreement with numerical simulations for this type of material. So I'll skip this one. And I think I'm almost done in time, so I'll try to say a few words for this final part, which is about oralization of vibroacoustic models. So again, oralization is about listening to models. So in wave field synthesis, the virtual sources, which are used in wave field synthesis, are usually very simple. They're point sources, monopoles, plane waves, so very simple objects. So we were interested in oralizing in space using wave field synthesis more complicated objects. And the less complicated among these more complicated objects were vibrating plates. So imagine this is a vibrating plate that radiates sound. A vibrating plate will radiate sound with a fairly complicated frequency response and a fairly complicated directivity pattern in space. And we wanted to oralize the sound field of such an object using wave field synthesis. And these small rectangles actually depict the loudspeakers of our wave field synthesis system in Sherbrooke. So we did that with this wave field synthesis system. So imagine the rear wall here is a big vibrating plate, vibrating object. Would it be possible to listen, both in terms of frequency content and directivity pattern, listen to the sound field of such a large object using our wave-field synthesis system? So we implemented that this is an example for a large plate which would be just behind the wave-field synthesis loudspeakers. These are the wave-field synthesis loudspeakers. So I forgot to mention here that we installed a line of microphones which were used for comparisons between what we actually reproduced and what the model predicts. So these are the monitoring microphones. And these are spatial impulse responses of the object. So in essence, when you strike a vibrating plate with a hammer, for example, at this point, you will create bending waves that will propagate in a plate to the end of the object, will bounce back, and so on. And as these vibration waves propagate, they radiate sound energy. And this is what we get. So these are spatial impulse response. This is the position along this microphone array, and this is time. So this shows the spatial impulse response, which is made of different wavefronts coming from the object and reaching the microphone array with different directions because of this complex sound radiation mechanism. And the left, just concentrate on the left. The left is the model. This is the model, and this is the experiment. This is what we measured in the lab. And as you can see, the spatial impulse response reproduced is quite similar to the target, to the modeled, with some other artifacts that are due to the reverberation of the listening space, the wave-field synthesis room, which of course are not present in the model. I'll drop that one. And the very last part, we move to the next step of trying to model even more complex objects. Maybe you are aware that in acoustics, we have now very, very sophisticated simulation tools, commercial softwares, finite element methods, boundary element methods, which can virtually model the sound field of any object. And so these software provide results in the form of, again, figures, numbers, plots, nice color maps, and so on. So the question was, is it possible to listen to the result of a finite element simulation or a boundary element simulation? So for complicated objects. So imagine this is for example, a cello, which is there, and you would like to listen to the sound field of this cello, both in terms of the frequency content and in terms of the directivity in space of the sound field. And again, we tried to do that using our wave-field synthesis system at Sherbrooke. So the master student, François Proux, did a quite fantastic work of creating all the workflow that start with the finite element, boundary element results, numbers, crushing these numbers and driving the loudspeakers of the wave-field synthesis to oralize the object in space. And this is just one example for, this is not a cello, sorry. This is a half cylinder. This is a half cylinder which sits there just behind the wave-field synthesis loudspeakers. Again, this is the impulse response. You strike this structure. It's a very reverberant structure. It's not very much damped, so it will have a very long vibration impulse response. It's quite small here. Again, this is the result of the model, the numerical model, and this is what we measured in the lab. So again, we're able to recreate quite accurately the structure of the impulse response in space. And this is a frequency response, so this is at one specific microphone location, and this shows the frequency response. Maybe it's not very super clear, but the gray, the very light one here is the simulation, and the blue is the measurement. So in terms of frequency response, you see that this object has a very peaky and complicated frequency response, and the wave field synthesis system was able to recreate this very specific type of frequency response. Okay, I probably went over a little bit. Huh? So time to conclude. So methods, technologies, hardware exist to physically reproduce sound fields, and you're well aware of that because here at CIRMMT you use many of these systems and approaches and technologies. I didn't really explain that in the course of my presentation, but there are mainly two different ways of using this system, which I call non-parametric and parametric. Non-parametric is simply means simply that we start with an actual spatial capture of a natural sound field, and we're trying to reproduce it in another setting using loudspeakers. The parametric use would be based on the addition of monophonic sources, which would be distributed in space by the user. So I hope I showed that there are many applications in engineering of these technologies. I showed a few for the spatial restitution of sound fields for acoustic comfort, sound quality evaluation, subjective testing. These can be wonderful tools. I didn't mention that, but the mock-up system, for example, was a fantastic system, was a fantastic tool to play virtual noise control scenarios. Philippe Aubert actually did that. He was able to use this aircraft cabin mock-up sound field recreation. By pushing a button, you can listen to what would happen if you have a sound package added to your aircraft structure. Okay, this is what I hear now. And this, again, back to the original one. You cannot do that physically, very easily. So these tools are wonderful tools to do that, actually. They're very useful for measurements. I'm really convinced that these multi-loudspeaker technologies have a future to do measurements and avoiding very complicated infrastructures, reverberant room, wind tunnels, and so on. And also the possibility to listen to models. And again, for designers, acoustic designers who use such commercial software for simulation, I think this could be a wonderful addition, the possibility to almost instantly be able to listen to the result, and again to play noise control, what-if scenarios. What if I modify this material, this dimension here, this and this. So this is it. Thank you for your attention.